Welcome to the Deep Dive. Today we're diving deep into the sources you've shared about one of the most iconic science books ever written, Stephen Hawking's A Brief History of Time.
That's right. And we have a fantastic stack of summaries and Q&A sections here, giving us a pretty good roadmap through some. Yeah, and it immediately sets up this great contrast between these profound questions and some of the earliest, more intuitive answers we came up with, like that often quoted story about the little old lady insisting the Earth is a flat plate on the back of a giant tortoise.
The tortoise story. It's a perfect, almost funny illustration of how science differs from just making things up, right?
Yeah.
Science asks, okay, interesting idea, but what's the evidence?
Exactly. And more importantly, what's the next question? What's the tortoise standing on? It's turtles all the way down, apparently.
It highlights that need for testability.
Precisely. The history of cosmology, which the sources trace beautifully, is really the story of asking those next questions and building models based on evidence. It starts with figures like Aristotle, who used careful observations, the shape of the Earth's shadow on the moon during an eclipse, or how the North Star's position changes as you travel.
Clever stuff, really.
Yeah, to prove the Earth was spherical, though he still put Earth at the center with his geocentric model.
And Ptolemy tried to make that geocentric model work better, adding complex spheres and orbits. But it always felt a bit, clunky.
Totally clunky. It even predicted the moon should sometimes appear twice as close as others, which clearly didn't match what people actually saw. You just look up and know that's not right.
Those mismatches, those little cracks, they eventually led to a revolution, didn't they?
They did. Copernicus proposed the heliocentric model, putting the sun at the center. Then Kepler figured out planets move in ellipses, not perfect circles, which was another big shift.
And then Galileo turns his new telescope to the sky and sees things no one had seen before, like moons orbiting Jupiter. That's huge.
Oh, absolutely huge. It's direct evidence that not everything orbits the Earth, shaking the very foundations of that old geocentric view.
It completely changed the perspective.
It really did. And then Newton arrived and provided this incredible unifying framework with his laws of motion and universal gravity, explaining why the planets move in those elliptical paths. It was a monumental leap.
But it still left questions, right? Like, if gravity is always attractive, why doesn't a static universe just collapse in on itself?
Exactly. That was a puzzle, which sparked debates about whether the universe was finite or infinite, often tied up with, philosophical and religious ideas at the time.
And here's where it gets really interesting in the modern era. Edwin Hubble, looking through telescopes in the 20th century, he observed that distant galaxies are moving away from us. And the farther away they are, the faster they're receding. He saw this through the redshift of their light.
Redshift, meaning the light waves are stretched out, indicating movement away from us, like the sound of an ambulance siren changing pitch as it passes.
So the universe isn't static, it's expanding.
A truly groundbreaking discovery. This expansion strongly implied that the universe was smaller, denser, and hotter in the past, pointing back towards the beginning, what we now call the Big Bang.
It fundamentally overturns centuries of thinking about a fixed, unchanging cosmos.
And the sources make a crucial point here about how science actually works. Theories aren't absolute truths carved in stone. They are models we build to predict observations. They have to be provisional, testable, and importantly, capable of being disproven. That's actually the strength of science.
It's about finding the best model that fits the evidence we have right now, not the final word necessarily.
Precisely. And this first chapter sets the stage for the ultimate goal of modern physics, finding a single, comprehensive theory, often called a unified theory.
The theory of everything.
Kind of, yeah. A theory that can reconcile Einstein's general relativity, which describes gravity and the large-scale structure of the universe, with quantum mechanics, which describes the weird world of atoms and subatomic particles.
Bringing together the really big and the really small.
Oh, okay.
Speaking of big ideas, let's move on to Chapter 2 and unpack how our understanding of space and time itself was completely revolutionized by relativity.
Right. This section starts by challenging another old idea, Aristotle's notion that heavier objects fall faster, which seems intuitive, but
isn't true. Galileo's experiments, famously described as perhaps dropping weights from the Tower of Pisa, though he likely used ramps, the sources say.
Yeah, probably ramps. But the point is, he showed that objects of different weights fall at the same rate if you can somehow get rid of air resistance.
That's a fundamental concept shift right there. And Newton built on this with his famous laws of motion: inertia, ephemer, and universal gravity.
And while Newton's laws implied there's no unique at-rest frame motion as relative, His framework still relied on the idea of absolute space and absolute time, like a universal clock ticking the same for everyone, everywhere.
A rigid backdrop for everything.
Exactly. But the sources show how modern physics chipped away at this. First, demonstrating that light speed isn't infinite. Ole Romer did this back in 1676 by watching Jupiter's moons.
How did he do that?
He noticed the timing of when Jupiter's moons disappeared and reappeared behind the planet seemed off depending on whether Earth was moving towards or away from Jupiter in its orbit. The difference was the time light took to cross that extra distance.
Clever. So light takes time to travel.
Finite speed. And later, Maxwell's equations unifying electricity and magnetism predicted light should always travel at a specific, fixed speed. Physicists expected there to be some medium, an ether, that light waves traveled through, like sound waves through air.
But the famous Michelson-Morley experiment in the late 1800s tried to detect this ether wind.
By measuring the speed of light in different directions relative to Earth's motion, and they found nothing. No difference.
The speed of light was constant no matter how the observer was moving. That must have been confusing.
Deeply confusing.
Yeah.
But it was a pivotal result that led directly to Einstein's special relativity in 1905. His key insight, or rather postulate, was twofold. The laws of physics are the same for all non-accelerating observers,
Okay.
and the speed of light in a vacuum is constant for everyone, regardless of their motion or the source's motion.
Okay, this is where things get truly weird and wonderful.
Mhm.
Because if the speed of light is a universal constant, then space and time can't be absolute, they have to be flexible.
Precisely. Consequences include mass and energy being equivalent, E inverse ITC. Mass is energy, essentially. They can convert into each other.
Which is the basis for nuclear energy.
Yeah.
And bombs.
Indeed. Also, nothing with mass can reach the speed of light. And crucially, measurements of time and distance change depending on your relative speed.
Time literally slows down for a moving observer compared to one standing still. That's the famous twins paradox, right?
Exactly. The twin who travels at high speed comes back and has aged less than the one who stayed home. Space and time are no longer fixed backdrops, they're interwoven and relative.
And Einstein wasn't done. He took it further with general relativity in 1915, his theory of gravity.
Which is even more radical in a way. Instead of gravity being a force pulling objects together, Einstein described it as the curvature of space-time caused by mass and energy.
Okay, explain that. Like a bowling ball on a trampoline.
That's the common analogy, yeah. Think of space-time as a flexible fabric. Put a massive object like a star on it, and it creates a dip or warp. Objects like planets don't orbit because they're being pulled by some invisible force. They simply follow the straightest possible paths called geodesics in this curved space around the star. They're just rolling along the curve.
Wow. Okay. And general relativity made testable predictions that Newton's theory didn't, right?
Yes, crucial ones. One was that light itself should bend as it passes near a massive object because its path follows the curved spacetime. This was famously confirmed during a solar eclipse in 1919 by observing starlight bending around the sun.
Incredible confirmation.
Absolutely. Another prediction is time dilation in a gravitational field. Clocks run slower in stronger gravity. This has also been confirmed with very precise atomic clocks at different altitudes.
So these theories completely redefine space and time. They aren't passive stages for events. They are dynamic entities woven together and influenced by the matter and energy within them.
Which leads us back to the expanding universe we mentioned earlier, because if space-time can curve and stretch,
Then the whole universe can stretch. Which brings us nicely to Chapter 3. When we look up at the night sky, we see stars in our own galaxy, the Milky Way. But telescopes reveal countless other galaxies, each containing billions of stars.
and a key challenge historically was figuring out just how far away these objects are. For nearby stars, we can use parallax, the apparent shift in the position as Earth orbits the sun.
Like holding your finger out and closing one eye, then the other.
Exactly. The nearest star, Proxima Centauri, is only about 4 light years away, which sounds close, but a light year itself is, trillions of miles, a vast distance.
For distant galaxies, Hubble had to use different methods, right? Like the brightness of certain types of stars within them.
Right, things like Cepheid variable stars. He used these standard candles to show that these fuzzy nebulae, as they were sometimes called, were actually incredibly far away, well outside our own Milky Way. There were entire other island universes.
But his most significant finding came from analyzing the light from these galaxies. He observed that their spectra,
That's the light broken down by wavelengths, like a rainbow.
right, those spectra were shifted towards the red end.
Yeah.
This red shift is an effect of the Doppler shift, meaning the light source is moving away from the observer.
Just like the pitch of that ambulance siren dropping as it moves away.
So most galaxies are moving away from us. And the clincher was that the speed they were receding was proportional to their distance. The farther away, the faster they're going. Hubble's law.
This was the direct observational evidence for an expanding universe. It fundamentally overturned the long-held belief in a static cosmos. It was revolutionary.
It seems obvious now, maybe, but the sources point out that even Newton, with his understanding of gravity, if the universe was static and infinite and full of stars,
It should have collapsed. Gravity pulls everything together, so why didn't it? Newton didn't really have a good answer. It took Hubble's observations centuries later to really shift the paradigm.
and based on general relativity, physicists like Alexander Friedman had already developed mathematical models describing a universe that could either expand or contract, depending on its overall density and energy.
Yeah, these Friedman models predicted different futures for the universe, maybe endless expansion, or maybe gravity wins eventually and it all collapses back at an eventual big crunch.
And the strongest evidence supporting the expanding universe and the Big Bang idea came later, quite unexpectedly, in 1965.
With the discovery of the cosmic microwave background radiation, the CMB.
Discovered how? Weren't they just trying to get rid of noise in a radio antenna?
Pretty much. Penzias and Wilson were working at Bell Labs trying to do radio astronomy, and they kept getting this persistent background hiss no matter where they pointed their antenna. They even cleaned out pigeon droppings, thinking that might be it.
Huh. Not the pigeons, then.
Nope. Turns out they'd accidentally detected the afterglow, the residual heat radiation from the incredibly hot, dense early universe, predicted years earlier by theorists like Gamow, Alpher, and Herman. It's a faint, uniform glow of microwave radiation filling the entire sky.
So this paints a picture of the universe starting at a point of apparently infinite density and space-time curvature, a singularity in the Big Bang.
According to classical general relativity, yes. The sources note that events before this singularity, if there was a before, have no consequences for us in that classical picture, as the laws of physics break down there.
The debate then turns to which Friedman model describes our universe. Will it expand forever, or will gravity eventually pull it back into a big crunch?
And current evidence, the sources mention, based on measurements of the expansion rate and the amount of matter and energy, seems to favor continued, maybe even accelerating expansion.
And this chapter highlights again the central challenge. General relativity, while powerful, breaks down at the Big Bang singularity. To understand that very first incredibly dense and tiny moment, we need to bring in the other pillar of modern physics.
Quantum mechanics. You need both the physics of the very large and the very small to tackle the origin.
The sources also briefly mention dark matter here, this mysterious, unseen mass detected only through its gravitational effects on galaxies and galaxy clusters.
Right. It seems to make up a huge chunk of the universe's mass, far more than the ordinary matter we see. It's crucial for understanding the universe's total density and structure formation, and ultimately, its fate. It's another reminder of how much we still don't know.
Speaking of the physics of the small, that takes us perfectly to Chapter 4, diving into the strange and often counterintuitive world of quantum mechanics.
Yeah, this is where things get really weird. Classically, physics was deterministic. Think of Laplace's vision. If you knew the precise position and velocity of every single particle in the universe at one moment,
You could predict the entire future and reconstruct the entire past with absolute certainty. Like the universe is one giant, predictable clockwork mechanism.
exactly, a deterministic dream. But classical physics ran into serious problems when applied to the atomic scale. For example, calculations predicted that hot objects, like a heated piece of metal, should radiate infinite energy across all frequencies, especially ultraviolet, the ultraviolet catastrophe, which clearly doesn't happen.
Right, you get instantly vaporized looking at a light bulb if that were true.
Pretty much. Max Planck solves this puzzle around 1900 by proposing that energy isn't continuous but comes in discrete packets, or quanta. An object can only emit or absorb energy in these specific amounts.
This was the birth of quantum mechanics, and it introduced a revolutionary idea that challenged determinism fundamentally. Heisenberg's uncertainty principle.
Yeah, formulated in 1927. This principle states you cannot simultaneously know both the exact position and the exact momentum, which is mass times velocity, of a particle with perfect precision. There's a fundamental limit.
So the more precisely you measure its position, the less precisely you can know its momentum and vice versa.
Exactly. And crucially, the sources emphasize this isn't just a limitation of our measuring instruments. It seems to be an inherent property of reality at the quantum level. The particle itself doesn't possess both a perfectly defined position and momentum simultaneously.
Wow. So that really marked the end of Laplace's dream of a perfectly predictable universe.
It did. It introduced a fundamental element of randomness or probability into physics.
Which famously led to Einstein's objection, God does not play dice. He was deeply uncomfortable with his inherent randomness.
He really was. He felt there must be some underlying hidden deterministic layer we just hadn't found yet. But so far, quantum mechanics has held up remarkably well experimentally. It shifted the focus from predicting exact outcomes to predicting probabilities, the likelihood of finding a particle here, or measuring this momentum there.
The best we can often do is predict a range of possibilities.
That's right. And the quantum world is full of other strange behaviors, like wave-particle duality.
Where particles like electrons can sometimes behave like distinct particles, little balls.
And other times behave like waves, spreading out and creating interference patterns, even if you send them through slits one at a time. It's as if each particle somehow interferes with itself.
Mind-bending. The sources briefly touch on this and how it relates to atomic structure. The idea of electron orbitals not as orbits but as probability clouds, and even Feynman's later, even more mind-bending idea of sum over histories.
Yeah, where a particle explores every possible path between 2 points simultaneously, quantum mechanics requires a whole new way of thinking.
The chapter also outlines the 4 fundamental forces that seem to govern everything in the universe.
Right. There's the gravitational force, the electromagnetic force, the weak nuclear force, and the strong nuclear force.
Gravity is the weakest, but acts over infinite distances, holding planets, stars, and galaxies together.
Electromagnetic force governs interactions between charged particles, electricity, magnetism, light. Much stronger than gravity at short distances.
Then the nuclear forces.
The weak nuclear force is responsible for certain types of radioactive decay. And the strong nuclear force is the strongest of all, binding protons and neutrons together inside atomic nuclei, overcoming the electric repulsion between protons.
And the sources mention a major achievement was unifying some of these forces.
Yes, a huge step. Salam and Weinberg, building on earlier work, showed that the electromagnetic and weak forces are actually different aspects of a single underlying force, called the electroweak force. This unification happens at very high energies.
Which leads to the ongoing quest for grand unified theories, or GUTs. What do they try to do?
They attempt to unify the electroweak force with the strong nuclear force, so bundling 3 of the 4 forces together.
And do these GUTs make predictions?
They do. They predict things like protons, which we normally think of as stable, might actually decay over incredibly long timescales, much longer than the current age of the universe, so it's hard to detect. They also offer explanations for mysteries, like why there seems to be way more matter than antimatter in the universe. Early in the universe, GUTs allow for slight differences in the way matter and antimatter behave, which could have led to a tiny excess of matter surviving annihilation. Our very existence, the fact that we're made of matter, is seen by some as possible evidence for these kinds of theories.
But the ultimate prize, the Holy Grail, still involves the 4th force.
Gravity, yes. The quest is for a theory of quantum gravity, unifying gravity, as described by general relativity, with the quantum rules of the other forces.
Why is that so important?
Because you need it to understand the universe in extreme conditions where both gravity and quantum effects are significant, like inside black holes or at the very moment of the Big Bang.
Which is the perfect segue into chapters 6 and 7, where we take a deep dive into the captivating and initially terrifying concept of black holes.
Absolutely. And the sources tell us this idea goes back surprisingly far, even before Einstein. John Michell in 1783, and later Laplace.
Using Newton's gravity.
Yeah, using Newton's theory and the idea that light was made of particles with mass, they reasoned that a star could be so massive and dense that its escape velocity would be greater than the speed of light, so light couldn't escape. A dark star.
But the term black hole itself is much more recent, right? Coined by physicist John Wheeler in 1969.
That's right, not Hawking, as sometimes thought. It's a much more evocative name.
So how do they actually form, according to modern physics? The sources explain stars are born from gas collapsing under gravity.
Balanced by the outward pressure from nuclear fusion burning hydrogen into helium in their core.
Right.
Like a continuous explosion pushing outwards against gravity pulling inwards.
But for very massive stars, They burn through their fuel much faster than smaller stars like our sun. And when they run out of fuel,
That outward pressure stops, gravity wins, the star collapses catastrophically under its own weight.
and what happens then depends on the mass.
Exactly. Scientists like Subramanian Chandrasekhar and Lev Landau calculated critical mass limits. Stars below a certain mass, after shedding outer layers, end up as dense embers called white dwarfs, supported by quantum pressure between electrons.
Okay.
More massive ones collapse further, crushing electrons into protons to form neutrons, ending up as incredibly dense neutron stars, maybe only a few miles across, supported by quantum pressure between neutrons.
But if the star is really massive, exceeding an even higher limit, sometimes called the Oppenheimer-Volkoff limit, or related to Oppenheimer and Snyder's work.
Then nothing we know of can stop the collapse. According to general relativity, it continues unchecked, crushing the matter down to a point of infinite density, a singularity.
And surrounding this singularity is the crucial concept, the event horizon.
Yes. The event horizon isn't a physical surface, it's a boundary in space-time around the singularity. It marks the point of no return. Once anything, including light, crosses that threshold, it cannot escape the black hole's gravitational pull.
The sources have a quote about it being like trying to outrun the police when they're already right behind you.
Yeah, the light rays at the horizon are trying to move outwards at the speed of light, but space-time itself is falling inwards so fast that the light just stays put, hovering at the edge, unable to escape.
And time behaves bizarrely near a black hole too, doesn't it?
Extremely bizarrely. From the perspective of an outside observer, time appears to slow down for an object falling towards the event horizon. If you watched an astronaut fall in, carrying a clock,
Their clock would tick slower and slower.
yes, and any signals they sent out would become increasingly stretched to longer wavelengths, redshifted, and the time between signals would get longer and longer. From your perspective, they would seem to slow down, fade, and effectively freeze at the event horizon, never quite crossing it.
But from their perspective, they just cross the horizon without noticing anything special at that exact moment.
Classically, yes. For a large enough black hole, the tidal forces might not be too extreme right at the horizon, they'd just pass through, but their fate inside, heading towards the singularity, is sealed.
This brings up the concept of singularities again. Didn't Roger Penrose propose something about them? The cosmic censorship hypothesis?
Right. General relativity predicts singularities, points where the theory breaks down. Penrose proposed that such singularities are always hidden from outside observers behind an event horizon. Nature, in a sense, shields us from the breakdown of predictability that occurs at a naked singularity. As a quote puts it, God abhors a naked singularity.
So black holes kind of tidy up the messiness of singularities.
In a way, yes, and the sources mention that from the outside, black holes are surprisingly simple objects. According to the no-hair theorem, once a star collapses, most of its complex details, its composition, magnetic fields, mountains, whatever, are radiated away or swallowed. The resulting black hole is described only by three properties: its mass, its rotation, angular momentum, and possibly its electric charge.
Mass, spin, and charge. That's it. No other hair.
Essentially, yes. Charge is usually thought to be negligible for astrophysical black holes, so it often boils down to just mass and spin.
Okay, so how do we actually find these things if they trap light? We can't see them directly.
True. The sources explain we detect them indirectly, through their powerful gravitational influence on their surroundings.
Like seeing a star orbiting. Nothing.
Exactly. Or, more commonly, seeing gas from a nearby companion star being pulled towards the black hole, forming a swirling, superheated disk around it called an accretion disk. This disk gets incredibly hot due to friction and emits intense X-rays, which we can detect.
And a famous example is Cygnus X1.
That's the classic example, yeah. A binary system where a visible star is orbiting an unseen companion whose mass is too large to be a neutron star, and it's a powerful X-ray source. It's widely accepted to be a black hole.
And more recently, we have gravitational waves, right?
Absolutely. The LIGO and Virgo detectors have directly observed the ripples in spacetime produced when two black holes spiral into each other and merge. This has opened up a whole new window onto black holes.
And there are supermassive black holes, too. Millions or billions of times the mass of the sun.
Yes, found lurking at the centers of most large galaxies, including our own Milky Way. These behemoths are thought to power the incredibly energetic phenomena known as quasars, seen in the early universe, where matter falling into the black hole releases enormous amounts of energy.
The sources even raise the possibility of much smaller black holes, not just from stars collapsing.
Right, so-called primordial black holes. These could have potentially formed in the very dense, chaotic conditions of the early universe shortly after the Big Bang from the direct collapse of overdense regions. They could range in mass from asteroids down to microscopic sizes.
Could we detect those?
It's an active area of research. We might detect their gravitational influence, perhaps through gravitational lensing, or
Really?
maybe through radiation they emit.
Which brings us perfectly to Chapter 7 and one of Hawking's most revolutionary discoveries. Black holes are not entirely black after all.
Exactly. This is where things get really profound. Hawking became fascinated by black hole thermodynamics in the early 1970s. Initially, building on work with Penrose, he helped prove a theorem stating that the surface area of a black hole's event horizon could never decrease in any physical process. It could only stay the same or increase.
That sounds familiar, like something we discussed earlier.
It does, doesn't it? It sounded remarkably similar to the second law of thermodynamics, which states that the total disorder, or entropy, in an isolated system never decreases. It always increases or stays the same.
So more area means more entropy.
That was the connection proposed by Jacob Bekenstein. He suggested that the area of a black hole's event horizon was actually a measure of its entropy, its hidden information content. The idea was that the total entropy, the entropy of stuff outside the black hole, plus the black hole's area representing its entropy, would never decrease.
How did Hawking react to that?
Well, the sources say Hawking was initially skeptical. If a black hole has entropy, thermodynamics says it must also have a temperature, and objects with temperature radiate heat. But black holes were supposed to be perfectly black, swallowing everything.
A contradiction.
Exactly. But in trying to rigorously disprove Bekenstein's idea by applying quantum mechanics near the event horizon, Hawking stumbled upon something astonishing.
Which was?
He found that black holes actually do emit radiation, precisely as if they have a temperature proportional to their surface gravity and inversely proportional to their mass. This is now called Hawking radiation.
Wow. So how does that work? How can something escape a black hole?
It relies on quantum weirdness near the horizon. According to quantum field theory, empty space isn't truly empty. It's fizzing with virtual antiparticle pairs that constantly pop into existence and then annihilate each other almost immediately.
Okay, virtual particles.
Right near the event horizon, it's possible for one particle of a pair to fall into the black hole while the other escapes. The particle that falls in can be thought of as having negative energy relative to an observer far away.
Negative energy.
It's a consequence of the intense gravity near the horizon. By swallowing this negative energy particle, the black hole actually loses mass. Remember, EMC was aver. To conserve energy overall, the escaping particle must carry away positive energy.
So from the outside, it looks like the black hole is emitting a steady stream of particles powered by this negative energy falling in.
That's the picture. It's a quantum effect happening right at the edge. And it has incredible implications.
Like what?
Well, first, it means black holes aren't truly eternal. They slowly lose mass and energy over time through this Hawking radiation.
They evaporate.
Yes, they evaporate. Very, very slowly. For large black holes, the lifetime of a solar mass black hole is vastly longer than the current age of the universe. But smaller black holes radiate faster and are hotter.
So a tiny primordial black hole could evaporate completely.
In theory, yes. As they lose mass, they get hotter and radiate even faster, potentially ending their lives in a final burst of high-energy radiation like gamma rays. Searching for these final bursts is one way people hope to detect primordial black holes.
So mass and energy aren't lost forever down the drain of a black hole. They are, in a sense, recycled back into the universe as radiation.
Exactly. The sources even have that line about the unfortunate astronaut eventually being recycled as thermal radiation. Information that falls in seems to come back out, albeit in a scrambled thermal form.
This discovery is incredibly significant then, because it shows a fundamental link between general relativity, describing the black hole's gravity, and quantum mechanics, describing the particle behavior near the horizon.
Absolutely. It's one of the most important results in theoretical physics because it happens right at the intersection of GR and QM. It strongly suggests that a full theory of quantum gravity might resolve the classical singularities predicted by GR alone, perhaps preventing them from forming or allowing information to escape.
It points the way towards that unified theory.
It really does. It shows quantum effects can have macroscopic consequences for gravity in these extreme situations.
Okay, shifting our focus back out to the grand scale. Chapter 8 revisits the origin and fate of the universe. in light of these new quantum ideas about gravity and black holes.
Right. Classically, based just on general relativity, the universe began at the Big Bang singularity, a point of infinite density where the laws break down. And its ultimate fate is maybe endless expansion, or maybe a collapse into a big crunch singularity, or maybe everything ends up inside black hole singularities.
More points where classical physics fails.
Exactly. But as we just discussed with black holes potentially evaporating, quantum effects suggest that maybe these absolute information-destroying singularities don't truly exist in a full quantum gravity picture. Mass and energy might return. This forces a rethinking of the very beginning and potential end.
The sources note that Hawking's renewed focus on cosmology was sparked partly by a conference at the Vatican in 1981.
Yeah, apparently the Pope cautions scientists against studying the moment of the Big Bang itself, suggesting it was the moment of creation, God's domain.
Which, knowing Hawking's personality perhaps, probably made him think, okay, challenge accepted, that's exactly what I need to study.
One can imagine. So the standard model for the universe's evolution after that initial moment is the hot Big Bang model. It describes a universe that was incredibly hot and dense, then rapidly cooled as it expanded.
Allowing particles to form, then eventually protons and neutrons, then light atomic nuclei like hydrogen and helium in the first few minutes, Big Bang nucleosynthesis.
Right, and then cooling further until atoms could form, releasing the cosmic microwave background radiation we observe today. Then gravity slowly pulled matter together, forming the first stars and galaxies over hundreds of millions and billions of years.
And this hot Big Bang model is strongly supported by evidence like the CMB, the abundance of light elements, and the expansion of the universe.
It's incredibly successful. But despite its success, the standard hot Big Bang model leaves some key questions unanswered. Why was the early universe so incredibly hot to begin with? Why is it so remarkably uniform on large scales? The CME temperature is almost perfectly the same in all directions.
And why does the expansion rate seem so precisely tuned? If it were slightly faster, maybe structures wouldn't have formed. Slightly slower, maybe it would have collapsed already. It seems finely balanced near a critical density.
These are called the horizon problem, the flatness problem, and the initial temperature problem. And they naturally lead to philosophical questions about initial conditions. Did the universe just start that way? Was it set up specifically?
Which spurred ideas like Alan Guth's inflationary theory in the early 80s. What's the core idea there?
Inflation proposes a very brief period of extremely rapid exponential expansion in the tiniest fraction of a second after the Big Bang. Like the universe ballooned incredibly fast.
How would that help?
Well, a tiny, smooth, causally connected patch could get blown up to be larger than the entire observable universe today. That could naturally explain the large-scale uniformity, the horizon problem, and also drive the geometry towards flatness, the flatness problem. Inflation stretches out any initial curvature.
And Andrea Linda developed models like chaotic inflation, suggesting that even from very messy random initial conditions, some patches of the universe could naturally undergo inflation and become smooth and flat like the part we observe.
Right. The source is, quote, Guth's idea that the universe could be the ultimate free lunch, potentially starting from almost nothing and using the negative gravitational energy to fuel the creation of positive matter energy during inflation.
Wow. Okay. And a major contribution Hawking worked on, often with Jim Hartle, tackled the very beginning itself, the quantum gravity and no boundary theory. This sounds profound.
It is a profound and quite radical idea. It tries to apply quantum mechanics to the universe as a whole right at the beginning. It suggests that maybe the universe is finite in space and time, but without a singular boundary or edge.
Like the surface of a sphere. It's finite, you can measure its area, but there's no edge you can fall off.
Exactly that analogy. The surface of the Earth is finite, but has no boundary. The no-boundary proposal suggests space-time might be similar, especially if you consider imaginary time.
Imaginary time, what's that?
It's a mathematical concept Hawking used, where time behaves more like another dimension of space. In this mathematical framework, the distinction between time and space blurs near the beginning, potentially allowing the universe to be smooth and rounded off, like the North Pole on Earth, a point where space-time begins, but not a singularity where laws break down.
So instead of starting at a point of infinite density, the Big Bang wasn't a singularity in this model. It was just the start of space-time itself.
That's a core idea, a universe that is self-contained without needing a separate moment of creation or a singular starting point where physics fails. It could, in principle, just be.
And did this no-boundary proposal make predictions?
Yes. The sources mention it made predictions about the nature of the tiny quantum fluctuations in the very early universe that would eventually seed the formation of galaxies. These predictions about the pattern of variations in the CMB temperature and the overall uniformity were later found to be consistent with observations from satellites like COBE and WMA.
So it's a potentially powerful idea, suggesting a way the universe could arise from the laws of physics alone, without needing special initial conditions imposed at a singularity.
Exactly. It potentially removes the need to ask what came before, because time itself might begin smoothly.
This chapter also brings up the anthropic principle again. Remind us what that is.
It's the idea that the properties of the universe we observe must be compatible with the existence of intelligent life capable of observing it. For example, if the fundamental constants of physics were slightly different, stars might not form, or chemistry might not work, and we wouldn't be here to wonder about it.
So we find ourselves in a universe that looks finely tuned for life because, well, we couldn't exist in one that wasn't.
That's the weak anthropic principle. It's a selection effect. Our observations are biased by the requirement that we must exist to make them. There are stronger versions too, but it reminds us that our perspective as observers is intrinsically linked to the nature of the universe we are trying to understand.
All these ideas, black hole radiation, inflation, the no-boundary proposal, they all push us towards needing that unified theory of quantum gravity to fully make sense of the universe's origin and ultimate fate.
They really do. And they blur the lines between physics and some of the deepest philosophical questions about existence and beginnings.
Which flows beautifully into Chapter 9, grappling with one of the most intuitive yet mysterious aspects of reality, the nature and direction of time itself.
Yeah, time. We experience it so directly, yet it's so hard to pin down. For centuries, the view was Newton's. Absolute time ticking away uniformly for everyone, everywhere. A universal metronome.
But relativity completely shattered that, didn't it? Showing time as relative to an observer's motion and gravity.
Absolutely. Time passes differently depending on where you are and how fast you're moving. There's no universal now.
And the sources mention how in theoretical models, using that imaginary time, like in the no-boundary proposal, the distinction between past and future, moving forward or backward in time, becomes ambiguous. It's treated more like a spatial dimension where you can go back and forth.
Right. Mathematically, it loses its unique directedness in that framework, unlike our everyday experience in real time.
Yet in our everyday lives, the difference between past and future is incredibly clear. A dropped cup shatters. It doesn't spontaneously leap off the floor and reassemble itself.
Exactly. We see processes happen in one direction only. And this distinction is deeply tied to the concept of increasing disorder or entropy.
Second law of thermodynamics again. It states that in any closed, isolated system, the total amount of disorder never decreases over time. It always stays the same or increases. A broken cup is more disordered than a whole one.
And this law defines a clear direction for time, the direction of increasing entropy. It provides an arrow pointing from past to future.
And the sources identify 3 arrows of time that seem to align in our universe.
Yes. There's the thermodynamic arrow, which is this direction of increasing disorder entropy.
Yep.
There's a psychological arrow, our subjective sense of time flowing forward. We remember the past, we anticipate the future, but we don't remember the future.
And the third.
The cosmological arrow, which is simply the direction of the universe's expansion. The universe is getting bigger over time.
And Hawking argues that these arrows must align, particularly if the universe started in a state described by the no-boundary condition.
Yes, his argument, especially linked to the no-boundary idea, is that the universe likely started in a very special, highly ordered, low-entropy state. As it expands, cosmological arrow, entropy naturally increases, thermodynamic arrow.
And how does the psychological arrow fit in? Why do we remember the past and not the future?
Hawking connects it to the thermodynamic arrow. He argues that the process of forming memories in our brains is a physical process that increases the overall disorder of the universe. To create the ordered state of a memory, our brains have to expend energy and radiate heat, increasing entropy elsewhere. So our psychological sense of time flowing is tied to the direction in which entropy increases.
So we experience time flowing in the direction the universe is getting messier.
Essentially, yes, we create tiny pockets of order, memories, within a larger system where overall disorder is increasing. And this requires the thermodynamic arrow to point in a consistent direction.
And he argued this alignment is necessary for intelligent life.
Yes, the argument is that conditions suitable for complex life, capable of processing information and forming memories, likely only exist when these arrows align specifically, in an expanding phase where entropy is increasing from an ordered beginning. A contracting phase, where entropy might decrease towards a big crunch, would likely be chaotic and unsuitable for organized life as we know it.
It's a fascinating link between the cosmos, physics, and our own consciousness. The sources do note some skepticism about whether the psychological arrow must align with the thermodynamic one, but it's a compelling idea.
It is. It suggests the universe's expansion is intrinsically linked to our ability to exist and perceive time as having a direction from past to future.
Okay, this deep dive into the arrows of time sets the stage for even more speculative but theoretically fascinating ideas in Chapter 10, wormholes and time travel.
Yes. Switching gears to pure sci-fi territory. Or is it? This chapter jumps right in, referencing writers like H.G. Wells, but explores whether traveling through time, particularly to the past, is actually allowed by the laws of physics as we currently understand them.
Classically, time was like a straight railway line, as one quote puts it, but relativity opened up possibilities. What if that line could have loops and branches?
General relativity is key here. Because it describes spacetime as being flexible and curved by mass and energy, it allows for the theoretical possibility of highly warped spacetime geometries. Back in 1949, the mathematician Kurt Gödel found an exact solution to Einstein's equations describing a rotating universe.
A universe that's spinning.
Yes, and in that specific theoretical universe, it would be possible to travel on a path through spacetime and end up back where and when you started. You could travel into your own past.
Wow, did Einstein like that?
Not particularly. It disturbed him, but it showed that GR in principle didn't forbid time travel. Other theoretical configurations, like maybe the region inside a rotating black hole, or hypothetical objects called cosmic strings moving past each other at high speeds, could also potentially warp space-time enough to create shortcuts.
Shortcuts through spacetime, like wormholes.
Exactly. Wormholes, sometimes called Einstein-Rosen bridges, are theoretical tunnels connecting distant regions of spacetime. If you could traverse one, you might end up not only far away in space, but also potentially at a different time. It's highly speculative, though.
Relativity already tells us time is relative to speed. The twins' paradox shows the traveling twin ages less, but it also says nothing can travel faster than the speed of light.
Right. C is the cosmic speed limit for travel through space. So, to enable time travel, especially to the past, you'd likely need to warp space-time itself to create a shortcut, a path outside normal space that gets you to a different point in time without locally exceeding light speed. Wormholes are one idea for such a shortcut.
But are they stable? Could you actually travel through one?
That's a huge problem. Most simple wormhole solutions in GR seem to collapse instantly or require exotic matter with negative energy density to hold them open.
Negative energy density, like the negative energy particles in Hawking radiation.
Possibly related, yes. The interaction with quantum theory is crucial here. Quantum effects, like the Casimir effect involving virtual particles between two close plates, can theoretically create regions of negative energy density. It's speculated that such quantum effects might allow for traversable wormholes or perhaps microscopic time travel.
But the sources mention that the laws of physics seem to conspire to prevent macroscopic objects or information from traveling back in time.
Yes, there's a strong sense among many physicists, including Hawking, that something prevents paradoxes. This leads to the classic time travel paradoxes, the grandfather paradox, for example. If you go back and prevent your grandfather from meeting your grandmother, how could you have been born to go back in the first place?
Right. How does physics deal with that?
There are different ideas. The consistent histories view, favored by some, suggests you simply can't change the past. Any action you take was already part of the history that led to you going back. You can't create a paradox because history is self-consistent.
So you might try to change things, but you'd fail.
Or your actions would turn out to be the very thing that caused the events you were trying to prevent. Another idea is the alternative histories, or many worlds, view from quantum mechanics, where traveling back creates a new parallel timeline, avoiding paradoxes in the original one.
But physics seems to lean towards preventing paradoxes in a single timeline.
There's the chronology protection conjecture, proposed by Hawking himself. It's not a proven theorem, but a strong hunch that the laws of physics themselves, perhaps through quantum gravity effects we don't fully understand yet, fundamentally prevent the formation of closed time-like curves, paths into the past, on macroscopic scales. History protects itself.
And perhaps the strongest empirical evidence against time travel to the past is, well,
We haven't been overrun by tourists from the future. If it were easy or even possible, you might expect some evidence of it by now.
huh. That's a fair point. So the sources conclude that while the possibility remains open within the framework of general relativity, particularly when quantum effects are considered, Hawking himself wouldn't bet on macroscopic time travel to the past being possible. He's quoted saying, "I'm not going to bet on it."
A characteristically cautious yet open-minded stance in the face of such mind-bending possibilities.
Which brings us logically to Chapter 11 and the overarching goal that ties so many of these concepts together, the quest for a unified theory.
Yes, the ultimate ambition. The goal is to find a single, complete, consistent theoretical framework that can describe all the fundamental forces and particles in the universe. It should encompass all our current successful partial theories, like general relativity and the standard model of particle physics, which includes quantum mechanics and the electroweak and strong forces, as approximations valid in certain domains.
The theory of everything dream again. As one quote from the sources says, one would hope to find a complete, consistent, unified theory.
This was Einstein's great obsession in his later years, trying to unify gravity with electromagnetism. But part of his difficulty, the sources note, was that he never fully accepted the probabilistic nature and weirdness of quantum mechanics. It just shows how incredibly hard it is to integrate such fundamentally different ways of describing reality.
Where does the main difficulty lie in combining GR and QM?
Well, GR is a classical theory describing gravity as smooth space-time curvature. QM describes the other forces in terms of discrete quanta and probabilities, operating on a fixed space-time background, usually. When you try to apply standard quantum calculation techniques, like summing over virtual particle contributions to gravity, the intense fluctuations of space-time at very small scales, predicted by combining the theories naively, lead to uncontrollable infinities in the calculations. The results become meaningless.
Like the infinities that plagued earlier quantum theories.
Similar, yes. Physicists developed a technique called renormalization to handle infinities in theories like quantum electrodynamics, QED, which describes electromagnetism. It involves mathematically absorbing the infinities into a redefinition of basic quantities like mass and charge. It works incredibly well for predictions, but
But it feels a bit like sweeping the problem under the rug.
to some, yes, it seems like a mathematical trick rather than a fundamental solution, and it relies on the theory having only a finite number of infinities to absorb. General relativity, unfortunately, appears to be non-renormalizable in the standard way it seems to generate new infinities at every level of calculation.
So that path didn't work for gravity.
And-
What other ideas emerged?
Well, there was interest in theories like supergravity, which tried to link particles with different spins using a new kind of symmetry called supersymmetry. It had some nice properties, but still faced problems with infinities and didn't fully work. Then, more prominently, starting seriously in the 1980s, came string theory.
What's the fundamental idea of string theory?
Instead of elementary particles being zero-dimensional points, string theory proposes they're actually tiny, vibrating, one-dimensional loops or segments of string. Different particles, like electrons or photons or gravitons, the hypothetical quantum of gravity, correspond to different ways these strings vibrate, like different notes played on a violin string.
And this somehow helps with gravity and infinities.
The hope, and some calculations suggest, is that because strings are extended objects, not points, they smear out the interactions at very small distances, potentially taming the infinities that plague point-particle theories of quantum gravity. String theory naturally includes a particle with the properties expected of the graviton.
But string theories often require extra dimensions, right? Beyond the 3 space and 1 time we experience.
Yes, that's one of the most striking features. For mathematical consistency, the earliest string theories required 26 dimensions. Later, superstring theories, incorporating supersymmetry, seem to work best in 10 dimensions, 9 space, 1 time. More recently, M-theory hints at 11 dimensions.
So where are these extra dimensions? Why don't we see them?
The standard idea is that they are compactified, curled up on an incredibly small scale, perhaps the Planck scale, far too small to be probed directly by current experiments. Imagine looking at a garden hose from far away. It looks like a 1D line. Only up close do you see its circular second dimension.
Okay, I can sort of picture that.
Yeah.
But this adds complexity.
Immense complexity. It raises the question, why do we only experience 4 large extended dimensions? And there seem to be a vast number of ways to curl up the extra dimensions, each leading to potentially different low-energy physics in our 4D world. This is the landscape problem in string theory, a potentially huge number of possible universes predicted by the theory.
Does the anthropic principle come into play here again?
It does. Some argue that maybe only in those configurations of extra dimensions that lead to our specific 4 large dimensions and the physical laws we observe can complexity and intelligent life arise. So we find ourselves in one of the rare habitable configurations within the string landscape.
The sources also note there isn't just one string theory, right?
Correct. Initially, there seemed to be 5 consistent superstring theories, plus the 11-dimensional M theory. But then physicists discovered dualities, deep mathematical relationships, suggesting that these different theories are actually just different descriptions of the same underlying fundamental reality, perhaps viewed from different perspectives or in different limits.
So maybe they are all facets of one deeper theory.
That's the hope behind M theory. It raises questions about what a final unified theory might even look like. Maybe it's not a single set of equations that works everywhere, but perhaps a web of interconnected theories or different mathematical formulations that apply best in different situations or energy regimes. As the sources quote, confidence in a theory comes from its mathematical consistency and its agreement with observations, even if it's complex.
So what's the future of this quest? Where might it lead? The sources suggest 3 broad possibilities.
Right. One is that we eventually find a complete, single, unified theory, the ultimate goal. A second possibility is that there isn't a single ultimate theory, but rather an infinite sequence of ever more refined theories that describe reality better and better at higher energies or smaller scales, but never reach a final endpoint.
Like peeling an infinite onion.
Kind of, yeah. And the third possibility is perhaps more unsettling. Maybe there is a fundamental limit to our ability to predict. Maybe some events in the universe are ultimately random and cannot be described by any deterministic theory, even a unified one.
So if a unified theory were found, what would the implications be? Would it mean we know everything?
Not at all. It would be a monumental intellectual achievement, revolutionizing physics and our fundamental understanding of the universe's building blocks and rules. It would change how we teach physics. But even with a complete set of fundamental laws, perfect predictability for everything would likely be impossible. The uncertainty principle from quantum mechanics would still hold. And applying those fundamental laws to complex systems like weather patterns or turbulent fluids, let alone biological systems or human behavior, would remain incredibly, perhaps intractably difficult.
So knowing the rules doesn't mean you can easily predict the outcome of the game, especially if it's a very complex game.
Precisely. The knowledge would enhance our comprehension of the cosmos immensely, but the intricate details of existence, the sheer complexity of emergent phenomena, and certainly understanding human nature would likely remain profound challenges.
And that brings us thoughtfully to Chapter 12, the conclusion, reflecting on this entire journey and the fundamental human drive that propels it.
Exactly. It comes back to that core human trait. We're deeply curious. We seem intrinsically driven to ask questions about the nature of the universe, our place within it, where it all came from, and why it follows the rules it does. It's a fundamental aspect of being human.
And theories, whether it's the ancient myth of the world being on a giant tortoise or the incredibly complex mathematical framework of superstring theory, are our attempts to build world pictures, coherent narratives that make sense of what we observe and experience.
Even when direct evidence for the deepest parts of the theory is hard or currently impossible to come by. The tortoise theory fails pretty quickly because observation tells us people don't fall off the edge of the world. It fails empirical tests. Modern theories are much more sophisticated, but the drive is similar.
Historically, the sources note, we moved from explaining phenomena with unpredictable spirits or deities to seeking regularity in nature. This led to the rise of scientific law and, eventually, scientific determinism, epitomized by Laplace's vision of a predictable cosmic machine.
If only you knew the initial conditions and the laws, you could know everything.
But as we've seen throughout this discussion, quantum mechanics and the uncertainty principle fundamentally challenge that complete determinism.
Yes. Quantum mechanics introduced inherent probability and limits on what can be known simultaneously. Science's task shifted, or perhaps was refined, to discovering the laws that govern reality within those fundamental quantum limits. As one quote suggests, science now aims to discover the laws that allow prediction up to the limits set by the uncertainty principle.
Gravity remains central to the universe's structure and key events like the Big Bang and black holes. But the combination of general relativity and quantum mechanics, especially through ideas like Hawking radiation and the no-boundary proposal,
Suggests a picture where the universe might not have originated from a classical singularity after all. It might be finite yet boundless, self-contained, without a definite beginning or edge in time where physics breaks down.
this possibility of a universe without a singular beginning or edge deeply impacts the philosophical or theological questions, doesn't it? Like Einstein's famous query about.
How much choice God had in constructing the universe. If the universe could arise naturally from physical law, without needing specific initial conditions set at a singularity, it changes the nature of that question.
And if we could find that complete, unified theory Hawking mused, it might be the ultimate triumph of human reason. He famously said it would be like knowing the mind of God.
Not necessarily in a personal theological sense, but understanding the complete set of laws that govern existence, the fundamental blueprint of reality.
Historically, the sources point out philosophy and science were deeply intertwined. Think of Aristotle. But they grew apart as science became more mathematical and technical.
Yes, philosophy tackled the why questions, while science focused more on the how. But perhaps future breakthroughs in fundamental physics, dealing with the nature of reality, time, and origins, might potentially bridge that gap again, allowing for more unified discussions about the nature of existence and our place in it.
The sources briefly remind us of some key historical figures in this scientific quest, like Einstein's broader political and social engagements beyond physics, Galileo's crucial conflict with church authority for prioritizing empirical observation over dogma, and Newton's foundational work alongside his sometimes contentious personality and debates.
It emphasizes that this scientific quest, while dealing with abstract ideas, is a deeply human endeavor carried out by real people embedded in their historical and social contexts.
Okay, so we've really traversed an incredible landscape here today, guided by the sources and Hawking's profound work synthesized within them. We've gone from ancient myths about tortoises
All the way down.
to the Big Bang, black holes that aren't quite black, the fuzzy reality of quantum uncertainty, and the ongoing, maybe never-ending quest for a single theory of everything.
We've seen how our understanding isn't fixed. It's a dynamic process, constantly evolving, replacing older pictures with newer, hopefully more accurate ones based on observation, experiment, and theoretical insight.
And the sources brilliantly highlight not just the amazing progress we've made, but also the deep mysteries that still remain, the profound questions that continue to drive scientists forward.
Absolutely. So, based on this deep dive, thinking about everything we've touched on, here's something for you, the listener, to consider. Given the probabilistic, uncertain nature of reality at its most fundamental level, as described by quantum mechanics, and the theoretical possibility suggested by ideas like the no-boundary proposal of a universe that is finite but utterly without boundaries or a singular beginning, what does that fundamentally mean for our very human sense of why things exist, why they are the way they are?
Does the scientific pursuit of a complete understanding ultimately reduce the mystery of existence?
Or does it perhaps just reshape it, maybe transforming it into something even more profound, more awesome in the true sense of the word?
A fascinating question to ponder. Thank you for bringing us this absolutely incredible material to deep dive into today. It's been mind-expanding.
It certainly has. A journey well worth taking.